Have you ever just stopped and, thought about how a single word can pack such a punch?
Hmm.
How one sound can unlock whole worlds of meaning across fields that seem, well, totally unrelated.
Yeah, like a hidden thread connecting things.
Exactly. And how that word might tap into something really deep in us, that human need for, I don't know, understanding, for order, especially when things feel a bit chaotic.
It's a powerful idea.
Well, today, that word is cosmos. And trust me, it's way, way more than just a fancy synonym for the universe.
Oh, absolutely. Much richer.
So this deep dive, it's going to be a journey.
Mm.
We're tracing the meaning, the idea of cosmos, from ancient philosophy right up to cutting-edge tech.
From Pythagoras to blockchains, essentially.
Got it. We're exploring how this one little term has been this constant anchor for us, for humanity's search for harmony, for structure, for meaning, whether we're gazing at stars or, believe it or not, mixing a drink.
It pops up in surprising places.
It really does. Okay, let's unpack this then. This deep dive is designed to give you a quick, solid grasp of what cosmos means across science, culture, technology, the whole shebang.
Think of it as a shortcut to understanding a fundamental human drive.
Exactly. Our mission really is to pull out the most important nuggets, the key insights, to show how we humans are always trying to organize things, to understand, to create harmony. Doesn't matter the field, doesn't matter the scale.
Looking for that pattern, that order.
Yes. And we want to get beyond just the surface definitions, right, to understand the why.
Deeper connections.
So get ready for, hopefully, a pretty fascinating trip. We're kicking things off in ancient Greece, thinking with the early philosopher.
The birthplace of the word itself.
Then we're launching into the, frankly, mind-bending scale of scientific cosmology. Think Big Bang, dark matter, all that good stuff.
The grandest stage.
We'll touch on those iconic popular science series, the ones that brought the universe into our living rooms.
Sagan, Tyson, changing how we see things.
Then, a fun detour. We'll investigate the surprisingly messy history of a classic cocktail.
Ah, the Cosmopolitan. More chaos than Cosmos in its origin story, perhaps.
Maybe so. Then a pause, a moment of quiet beauty, looking at the symbolism of a simple garden flower.
The Cosmos flower, aptly named.
And finally, we're zooming into the digital age, looking at the architecture, the ambition of a new cryptocurrency frontier.
Bringing order to the blockchain world.
You should expect some real aha moments as we connect these dots. They seem so different, but there's this universal thread running through them.
It's all about finding or making order.
Okay, so our journey into the idea of cosmos. It doesn't start with a giant telescope. It starts with a philosopher.
Right back in ancient Greece.
The word itself, it's got these deep philosophical roots, usually credited to Pythagoras way back 6th century BC.
Imagine that time, trying to make sense of the world, the natural forces.
Exactly. And Pythagoras, he uses cosmos to describe something specific.
Yeah.
An orderly or harmonious universe. It wasn't just a label, was it?
Not at all. It was a statement, a profound declaration, really, that reality wasn't just random. It had structure. It had beauty.
And the etymology itself is, well, it's really revealing here.
It absolutely is. The Greek word cosmos, that's K-O-S-M-O-S, it's the direct opposite, the philosophical counterpoint to chaos, C-H-A-O-S.
Chaos being.
Yeah.
Just nothingness, formlessness.
Pretty much. Think of Hesiod's theogony, that primordial state before anything was created, a gaping void, undifferentiated. Cosmos, on the other hand, represented an ordered system, something with structure, something intelligible, and, crucially, something beautiful.
So right from the start, you have this fundamental split in how you can view reality.
Exactly. Chaos versus order. Formless void versus structured whole. It really set the stage for how Western thought perceived the universe not as just a jumble, but as an organized, potentially understandable entity.
It gets even richer when you look at the verb it comes from.
Yes. The Greek verb has this fascinating dual meaning. It means both to put in order, like arranging things.
Tidying up.
Right. But it also means to adorn, to make beautiful.
Ah, so it's not just functional organization. It's about aesthetics, too.
Precisely. It highlights this inherent link between structure and beauty. Think about Greek art, architecture. The Parthenon, for example. The symmetry, the proportions.
The golden ratio. All that.
Yes. They weren't just building shelters. They were creating physical expressions of what they saw as cosmic order and harmony. Beauty wasn't separate from order. It was a consequence of it.
That duality seems really important.
It's crucial. This ancient worldview didn't just see reality as a bunch of disconnected bits and pieces. It defined it as a homogeneous, ordered whole.
Homogeneous meaning uniform, consistent.
In the sense of being governed by consistent principles, yes. It offered a framework, a meaningful context for human experience. It suggested the universe was fundamentally intelligible, harmonious, not just random chaos.
Which must have provided some sense of security, right?
Yeah.
Knowing the world wasn't totally arbitrary.
Absolutely. A sense that things made sense, that there was an underlying order you could potentially understand, admire, maybe even replicate in human society and creations.
Okay, let's jump forward. A long way forward. Millennia, really. While those early thinkers saw this unified cosmos,
This intelligible whole.
modern Western culture, particularly post-Enlightenment, often started drawing more lines, didn't it?
We did tend towards more dualistic thinking, yeah. Separating things like subject and object, mind and matter, humanity and nature, compartmentalizing reality in a way.
Did that original sense of cosmos get lost then?
Not entirely. And that's what's fascinating. Despite that philosophical shift towards dualism, the core idea of cosmos, that search for unity and order, it actually persists.
Also?
Well, you still see it today. Think about religious mystics seeking oneness with the universe, or physicists searching for a grand unified theory, a theory everything.
Right, trying to tie all the forces together.
Exactly. They're both, in their own ways, engaging with the cosmos, trying to grasp its unified nature. And for the modern scientist, the astronomer, the physicist, cosmos has a very specific meaning now.
More technical.
More technical, yes, empirically grounded. It means the entire physical universe considered as a unified whole. The focus is on an ordered system, explainable through physical laws, observation, mathematics.
So it's like a direct descendant of that Greek idea, discerning order from chaos.
In a way, yes. It's the same fundamental quest, but the tools have changed dramatically. We've swapped pure philosophy for empirical observation, rigorous experiment, the language of calculus and relativity. But the goal, still understanding that ordered whole.
So what does that really mean for us, for you listening? It means science isn't just about collecting boring facts.
Definitely not.
It's about tackling those huge fundamental questions we've always asked. Where do we come from? What is this place? Where do we fit in?
And the specific branch of science dedicated to those questions about the universe as a whole is cosmology.
Right. Cosmology.
It's the scientific study of the origin, evolution, and overall structure of the universe. It's a massive field, really. It connects the tiniest subatomic particles to the largest structures we know, like galaxy superclusters.
And it stretches across time, too, right? From the very beginning to, well, whatever the end might be.
Exactly. From the first fractions of a second to billions of years in the future. And cosmologic theories, like the Big Bang, they give us a scientific framework for answering those deep philosophical questions about our origins and our place.
So it really bridges that gap between hard science and, well, the big why questions.
It does. It's where the how of science meets the why of philosophy. And often answering a scientific question in cosmology opens up brand new philosophical ones. It's a continuous dialogue.
Okay, so when we talk cosmology, the origin story, the dominant model, the one most scientists agree on, is the Big Bang theory.
That's the one. Though the name itself was actually coined almost mockingly by astronomer Fred Hoyle back in '49. He didn't buy it. He favored a steady-state universe.
Oh, really? I didn't know that. But the name stuck it.
It did. The actual theory, the foundational idea, came earlier from a Belgian priest and physicist named Georges Lemaitre in the 1920s. He called it the hypothesis of the primeval atom.
A primeval atom. So the core idea is what? Everything from a single point.
Essentially, yes.
Yeah.
The theory proposes that the universe began in an incredibly hot, incredibly dense state, often called a singularity, and it's been expanding and cooling ever since, from that point-like state to the vast, relatively low-density universe we see today.
And it's not like stuff exploding into space, right? It's space itself.
Expanding, exactly. The fabric of space-time is stretching, and it carries the galaxies along for the ride. It's a crucial distinction.
And we can actually see evidence of this. It's not just math.
Oh, absolutely. The evidence is written across the sky. One of the most crucial pieces, maybe the most elegant, is the redshift of distant galaxies.
Redshift, like the Doppler effect for light.
Precisely. Imagine a siren. As it moves away, the sound waves stretch out, the pitch drops. With light, as distant galaxies move away from us, the light waves stretch, shifting towards the red end of the spectrum.
And this tells us they're moving away.
Yes. And not just that. Edwin Hubble, back in 1929, made the key observation. The farther away a galaxy is, the faster it appears to be moving away from us. There's a direct relationship.
That's Hubble's law.
That's Hubble's law. Velocity is proportional to distance, v h 0. It's a cornerstone. It strongly implies a universe that started small and has been expanding ever since.
Like dots on an inflating balloon moving away from each other?
That's the classic analogy, yeah. Useful for visualizing, though you have to remember it's space itself stretching. And this redshift observation, it fits perfectly with Einstein's theory of general relativity.
Ah, Einstein comes into it.
Big time. In fact, his equations initially predicted an expanding or contracting universe. But Einstein at the time couldn't accept it. He preferred a static cosmos. So he added this fudge factor, the cosmological constant, to force his equations to allow for a static universe.
A fudge factor, really?
Yep. He later called it his biggest blunder. When Hubble showed the universe was expanding, the constant wasn't needed for that purpose anymore, though it's made a comeback recently for other reasons related to dark energy.
Wow. So redshift plus other evidence?
Yeah.
Like the afterglow?
Exactly. The cosmic microwave background radiation, the CMB, that's the faint heat left over from the Big Bang, detected uniformly across the sky. And also, the observed amounts of light elements like hydrogen and helium match predictions for what would have been forged in the first few minutes. That's called primordial nucleosynthesis. All these pieces fit together remarkably well to support the Big Bang model.
Okay, so the Big Bang sounds pretty solid. But you mentioned earlier there were problems, head scratchers.
There were, yes. Despite all the supporting evidence, the basic Big Bang model, as initially understood, ran into some tricky issues. It predicted a universe that should look lumpier, less uniform than what we actually observe.
How so? What were the main problems?
Well, there were three big ones. First, the flatness problem. Observations show our universe is geometrically very, very close to flat, like incredibly flat.
Flat meaning not curved, like Euclidean geometry works over vast distances.
Exactly. But according to general relativity, for the universe to be this flat today, its initial density right after the Big Bang had to be tuned to an unbelievable precision, like accurate to dozens of decimal places. Any tiny deviation would have caused the universe to either collapse back on itself almost immediately or expand so fast that no stars or galaxies could ever form. It seemed way too coincidental, too fine-tuned.
Okay, that sounds unlikely. What else?
Then there's the horizon problem. When we look at the cosmic microwave background, the temperature is astonishingly uniform in all directions, to within tiny fractions of a degree.
Right, the afterglow is smooth.
Super smooth. But here's the problem. Regions on opposite sides of the observable universe are so far apart now that light hasn't had time to travel between them since the Big Bang. They were never in causal contact, never able to exchange heat or information to reach the same temperature. So how did they end up so perfectly thermalized? It seemed to violate basic causality.
Huh. How could things be the same temperature if they never talk to each other?
Exactly. And the third one was the monodipole problem. Certain theories that try to unify the fundamental forces grand unified theories, or GUTs, predict the existence of exotic, super heavy particles called magnetic monopoles. Basically, isolated north or south magnetic poles.
Like a magnet with only one pole.
Kind of, yeah. And the standard Big Bang model predicted these should have been created in huge numbers in the early universe and should still be around. But we've never detected a single one. Where did they all go?
Okay, flatness, horizon, monopoles. Those sound like pretty fundamental issues. Did people start thinking maybe the Big Bang was wrong after all?
That's a great question. It definitely caused a stir. But the evidence for the Big Bang, the expansion, the CMB, the light elements was just so strong. So rather than throwing the whole theory out, the scientific community looked for ways to refine it, to add something that could solve these puzzles while keeping the core successes.
Science in action. Don't scrap it, fix it.
Pretty much. And this led to the development of inflationary models, primarily championed by Alan Guth and others in the early 1980s.
Inflation, what does that involve? Blowing the universe up even faster.
In a nutshell, yes. Inflation proposes an incredibly brief period, like a tiny fraction of a second after the very beginning, where the universe underwent a burst of exponential expansion, much, much faster than the normal expansion we see today.
Exponential, like doubling in size over and over really quickly.
Extremely quickly, and this rapid stretching does something amazing. It elegantly solves all three problems.
How? Let's start with the horizon problem. How does inflation fix the temperature issue?
Well, before inflation kicked in, The region that would eventually become our entire observable universe was actually microscopically small, small enough for everything within it to have been in causal contact, to have interacted and reached the same temperature. Then whoosh, inflation stretched this tiny uniform patch to enormous scales almost instantly, preserving that uniformity over vast distances we see today.
Ah, so they were close enough to talk, then got flung incredibly far apart. What about flatness?
Inflation flattens the universe automatically. Think about the surface of a balloon. If you inflate it to a gigantic size, any small patch on its surface will look almost perfectly flat, right? Inflation does the same thing to the geometry of spacetime. It stretches out any initial curvature so effectively that the universe appears flat to us now, regardless of its initial shape. No fine-tuning needed.
Okay, that makes sense. And the missing monopoles.
Inflation solves that by dilution. If monopoles were created before or during inflation, that immense stretching of space would have spread them out so thinly that the chance of finding one in our observable universe today becomes practically zero.
Wow. So one mechanism, this incredibly rapid expansion, solved three major problems.
Yeah.
It's neat, almost too neat. Does that raise eyebrows?
That's a fair point. Some scientists do wonder if it's a bit ad hoc, designed specifically to fix the problems. But inflation isn't just a convenient story. It makes specific, testable predictions.
Like what?
For instance, it predicts the universe should be almost perfectly flat, which our best measurements confirm. It also predicts a very specific pattern of tiny temperature fluctuations, slight variations, in the cosmic microwave background, the seeds of future galaxy formation. And the patterns observed by satellites like WMAP and Planck match the predictions of inflationary models with stunning accuracy.
So there is evidence supporting it, beyond just solving the problems.
Yes, strong indirect evidence. While we haven't directly detected the inflaton field, the hypothetical field driving inflation, the concept is incredibly powerful and fits the data remarkably well. It's a prime example of how science progresses. A core theory faces challenges. New ideas are proposed to refine it. These ideas make predictions, and those predictions are tested against observations. It makes the overall picture stronger, more detailed.
It's like finding a flaw in a grand blueprint. But instead of scrapping the whole thing, brilliant minds figure out how to add a new, elegant feature that makes it even stronger.
That's a great way to put it.
But even with inflation, our cosmic story, it's
Yeah.
far from complete, isn't it? In fact, some of the biggest pieces seem to be missing.
That's putting it mildly. The ongoing quest to map out the cosmos has led to one of the most profound and humbling discoveries in modern science. Everything we can actually see, all the stars, galaxies, planets, gas, dust, all the ordinary baryonic matter.
The stuff we're made of.
Exactly. All of that makes up only about 4%, maybe 5% if we're generous, of the total mass and energy content of the universe.
Wait, only 4 or 5%? That's tiny.
It's minuscule. The vast majority, around 95 or 96%, consists of two components that are completely invisible to us. They don't emit light, absorb light, or scatter light. We call them dark matter and dark energy.
Dark matter. I've heard of that.
Yeah.
What exactly is it supposed to be?
Well, we don't know exactly what it is, but we know it's there because we see its gravity in action. About 26% of the universe's total inventory is thought to be dark matter.
So, more than 5 times the amount of normal matter.
That's right. And its existence is inferred purely from its gravitational pull. For example, look at galaxies rotating. The stars way out on the edges are moving much faster than they should be if only the visible matter stars and gas was providing the gravity. They should fly off into space.
But they don't.
They don't. There must be a huge invisible halo of extra mass surrounding the galaxy, providing the extra gravity needed to hold those outer stars in orbit. That's dark matter.
And it affects more than just single galaxies.
Oh, yes. We see its effects in the way galaxy clusters bend the light from objects behind them, gravitational lensing. The amount of bending tells us there's far more mass present than we can see in stars and gas. And on the largest scales, dark matter acts like invisible scaffolding, creating the gravitational framework upon which the entire cosmic web of galaxies and clusters formed. Without it, the universe wouldn't have the structure we observe today.
So it's essential, it's everywhere, but we can't see it and don't know what it's made of. What are the candidates?
The leading candidates are hypothetical particles that don't interact strongly with light or normal matter. Things like WIMPs, weakly interacting massive particles, or possibly much lighter particles called axions. There are huge experiments running deep underground, trying to directly detect these particles when or if one happens to bump into a detector nucleus. But so far, no definitive detection.
Mind-bending. So it's 26% dark matter, 4% normal matter.
Mm.
What's the rest? The biggest chunk?
That would be dark energy. And if dark matter is mysterious, dark energy is
Well, it's deeply baffling. It makes up the remaining 70% of the universe.
70%. And what does it do?
If dark matter acts like cosmic glue pulling things together, dark energy does the opposite. It acts like an anti-gravity force, pushing space-time itself apart and causing the expansion of the universe to accelerate.
Accelerate. Wait, I thought gravity should be slowing the expansion down.
That's what everyone thought, too. It was a huge shock when, in the late 1990s, two independent teams studying distant supernovae discovered they were dimmer, and therefore farther away than expected. The only explanation was that the universe's expansion hasn't been slowing down, it's actually sped up over the last few billion years.
Wow. So something is actively pushing the universe apart faster and faster.
Exactly. And that something is what we label dark energy. The leading idea is that it might be the energy inherent in empty space itself, Einstein's cosmological constant making a comeback, but its true nature is one of the biggest unsolved mysteries in all of physics. So let me get this straight. 4% is us and everything we see. 26% is invisible stuff holding things together. And 70% is even more mysterious invisible stuff pushing everything apart at an accelerating rate.
That's the current cosmic inventory, yes. It's a profound shift in perspective. The cosmos we've studied for centuries is just the tip of the iceberg. The vast majority is unknown, unseen, yet dictates the universe's structure and ultimate fate.
It really makes you wonder, what does our idea of an ordered universe, a cosmos, even mean if 96% of it is a complete mystery that controls everything?
That's the big question, isn't it? It certainly challenges our sense of understanding and order. It shows us how much more there is to discover.
Okay, let's shift gears a bit. From the sheer scale and mystery of the physical universe to, well, how we humans try to grasp it and share that understanding.
The communication of cosmology.
Exactly. And there was this real landmark moment, a watershed moment for science on TV back in 1980, the documentary series Cosmos, A Personal Voyage.
Ah, Carl Sagan. An absolute icon.
Truly. This 13-part series, written by Sagan, Andrewian, and Steven Soter, it wasn't just a show, it was a global event, broadcast in over 60 countries, seen by 500 million people.
The numbers are staggering. And Sagan's approach was unique. It really was a personal voyage. He wasn't just reciting facts, he was sharing his own sense of wonder, weaving together astronomy, history, biology, philosophy.
Yeah, it had this poetic, almost philosophical tone. He had this earnest confidence, this way of inviting you to think about the big questions.
Yeah.
Billions and billions.
He made the universe feel accessible, awe-inspiring, and deeply relevant to us as humans. And the visuals, for the time, were revolutionary.
The ship of the imagination,
Yeah.
sailing through nebula, walking on models of planets. It felt immersive.
Groundbreaking special effects back then. It gave you the illusion of being there with him.
For so many people, myself definitely included, that show was our first real deep dive into the universe. Sagan felt like this incredibly knowledgeable, enthusiastic friend guiding you through it all. It wasn't just educational, it felt important. Transformative, even.
It absolutely was. It set a benchmark for science communication that still resonates today, which leads us to the follow-up decades later.
Right. Over 30 years later, the idea was to bring back the foundation of science to network television, but for a whole new audience.
And so we got Cosmos, a Spacetime Odyssey in 2014, hosted by astrophysicist Neil deGrasse Tyson.
And the connection there is amazing, isn't it? Tyson often talks about how meeting Sagan as a teenager inspired him to go into astrophysics in the first place.
It's a wonderful full-circle story, a true passing of the torch.
The new series, it gets some of the iconic elements, right? The ship of the imagination, the cosmic calendar.
Yes, it followed the original format loosely, but obviously the information was updated with decades of new discoveries, exoplanets, dark energy, the latest from Mars rovers.
And the visuals got a massive upgrade. Lots of slick CGI, animation.
Extensive computer-generated graphics, yeah.
It
It was visually spectacular, tailored for a modern audience used to high production values.
Comparing the two series side by side, what does that tell us about how science communication has changed?
It reviews a really interesting evolution, I think, that mirrors broader shifts in media and culture. Sagan's original was very much defined by his unique personal style. It was slower paced, more contemplative, philosophical. It assumed an audience willing to engage deeply, maybe without needing constant visual stimulus.
It felt like you were settling in for a thoughtful exploration.
Exactly. Tyson's series, while excellent and praised for its updated science and clear explanations, adopted a more conventional, faster narrative style. More cuts, more CGI spectacle, perhaps aimed at holding the attention of an audience used to a quicker media metabolism.
So adapting to the times, essentially.
Right. It shows that communicating complex science effectively in the 21st century often means adapting the medium, the pacing, the visual language to meet the expectations of a contemporary, visually sophisticated audience.
Does something get lost in that translation, though? That move from a personal voyage to a Spacetime Odyssey?
That's the debate, isn't it? Does the increased visual polish and faster pace come at the cost of some of that deeper philosophical contemplation Sagan fostered? It's not just about different hosts. It reflects how our relationship with information, with media, with attention spans has evolved over those decades.
And there's another layer to this, a detail that often gets missed about the original Sagan series.
Ah, you mean the re-edit?
Exactly. The version most people know, the one readily available today, isn't the one that aired in 1980. It's a special edition from 1990.
Digitally remastered, but also significantly re-edited for commercial TV standards at the time.
And the changes weren't trivial, were they?
Not at all. They replaced about half of the original visual effects and about a third of the music. That fundamentally changed the pacing, the timing, the whole feel of the show.
So the original vision is kind of hard to access now.
Largely, yes. It highlights how media production itself shapes the legacy of a cultural work. The narrative gets subtly tweaked, optimized for different formats or audiences, sometimes for commercial reasons.
So the cosmos that lives in our collective memory might not even be the original broadcast version.
For many people, probably not. It's a reminder that even our cherished cultural touchstones can be reshaped, re-edited over time. Much like our scientific understanding keeps evolving, right? Our memory of the past isn't always fixed.
It makes you think about preservation, about original intent versus adaptation, a whole other kind of order being imposed, maybe.
That's a fascinating way to put it. The order of the archive, the order of the commercial edit versus the original creative order.
Okay, speaking of imposing order, sometimes deliberately, let's take a completely different turn, from the vastness of space and TV adaptations to something much smaller, much wetter.
Where are we going now?
To the bar. Let's talk about the Cosmopolitan cocktail.
The Cosmo. Pink, stylish. Definitely seems ordered.
It does. It's a perfect example of how that word cosmos can apply even to mixology, creating a sophisticated, orderly blend from different ingredients. But its history,
Oh boy.
not so orderly. Not remotely. It's described as a chronological web of competing claims, a real tangled origin story.
Okay, I'm intrigued. Lay it on me. Who claims they invented the Cosmo?
Well, first off, there's an older drink with the same name. A Cosmopolitan daisy shows up in a 1934 cocktail book.
1934, wow. What was in it?
Gin, Cointreau, lemon juice, and raspberry syrup. So similar idea, bright, balanced Cosmopolitan, but gin-based, not vodka. An early hint, maybe?
Interesting.
A precursor. Then fast forward to the 60s, Ocean Spray was pushing cranberry juice, right? They promoted a drink called the Harpoon.
Ocean Spray, okay.
It was basically vodka or rum, cranberry juice, maybe some lime. Not the Cosmo, but it established that vodka cranberry base that became key later on, setting the stage.
So who claims the modern pink version?
Okay, here's where it gets messy. One claim comes from Neil Murray, a bartender in Minneapolis around 1975. He says he added a splash of cranberry to a kamikaze that's vodka, lime, triple sec.
Right, a standard shooter.
And supposedly, when someone tasted it, they said, "How cosmopolitan." So he claims he coined the name right then.
Plausible story, but not the only one.
Not by a long shot. A very strong, widely cited claim comes from Cheryl Cook, a bartender in South Beach, Miami in the mid-'80s.
South Beach makes sense for a stylish pink drink.
Her story is she specifically wanted to create something visually appealing, oh so pretty in pink, served in a martini glass to look sophisticated. Her recipe used absolute citron vodka, triple sec, lime, and cranberry. She was focused on that aesthetic order, that visual appeal.
That sounds very close to the modern Cosmo.
It does. But then, the version that really became the international standard is often credited to Toby Cecchini in New York at the Odeon around 1989.
Okay, another contender.
He, along with Melissa Huff-Smith-Roth, supposedly perfected the recipe using absolute citron, Cointreau, a specific brand of triple sec, fresh lime juice, and cranberry. That's the formula most people recognize globally. So Minneapolis, Miami, New York, it's all over the map.
It really is. But you know what probably mattered more than any single inventor?
Let me guess. Sex in the City.
Bingo. Late 90s HBO. The show didn't invent the drink, but it made it an absolute icon. Suddenly, the Cosmo wasn't just a cocktail. It was a symbol of urban sophistication, female friendship, modernity. That cultural moment completely overshadowed the murky origins.
So the narrative became more important than the actual history.
Absolutely. It shows how mass media can define the legacy of something. The idea of order here isn't about historical fact, it's about the creation of a balanced, appealing form, the drink itself, and then the imposition of a cultural narrative that gives it a specific meaning and fame. We crave that simple origin story, even if the reality is a chaotic mess of claims.
From crafted cocktails to, well, natural creations, the word cosmos also has a much more direct and frankly beautiful application than the natural world.
You mean the flower?
The cosmos flower, exactly. Those lovely daisy-like flowers you see in gardens, lots of vibrant colors, really popular sunny weather plants.
And the name isn't just a coincidence, is it?
Not at all. It comes directly from that Greek root, kosmos, meaning order, harmony, but also specifically beautiful or ornament. It's a direct link back to those philosophical origins.
Connecting natural beauty straight to the concept of order.
And if you actually look at the flower, it embodies that order visually, doesn't it? The symmetrical form, those petals, often 8, following Fibonacci patterns, sometimes radiating so neatly from the central yellow disc.
A perfect little microcosm of structure and harmony. You see that mathematical regularity that often underlies natural beauty.
And that visual order, that structured beauty, is directly reflected in its symbolism.
Right, in floriography, the language of flowers. The cosmos flower stands for, well, order and harmony, directly reflecting its form and name.
But also other related ideas.
Yes, things like peace, tranquility, balance, but also innocence, modesty, and joy. Its presence is meant to evoke a sense of natural equilibrium and simple beauty.
It feels like a really purposeful connection. The name, the form, the meaning, they all line up perfectly.
It's not arbitrary at all. Naming the flower Cosmos was an act of recognizing its inherent order and beauty and then assigning symbolic meaning based on that recognition. It represents peace because its very form embodies that ordered harmony.
A tangible, beautiful example of that abstract idea of cosmos made real in nature, and how we use language to acknowledge and amplify that order.
Exactly. A little piece of cosmic order right there in the garden.
Okay, one more big jump from the garden back to the cutting edge. Let's go to the digital realm.
The final frontier.
Maybe. That ancient idea of cosmos creating an orderly, harmonious system, it's been totally reimagined for decentralized technology. Case in point, the Cosmos Atom cryptocurrency protocol.
Ah, yes, the Internet of Blockchains.
That's their big pitch. And it's all about bringing order to what can be a very fragmented, disconnected digital world. You know, historically, most blockchains were like isolated islands. They couldn't easily talk to each other or exchange value.
Right, which led to problems like slow transactions if you wanted to move assets between chains, limited scalability, just a general lack of interoperability. It kind of hampered the whole vision of a seamless, decentralized web.
So Cosmos aims to fix that, to connect the islands.
That's the core mission. Enable different independent blockchains to communicate and interoperate securely and efficiently without needing a centralized middleman.
Which raises that interesting question again. Can you really build a cosmos, an ordered system, out of all these independent, sometimes chaotic digital ledgers?
Right.
It's the cosmos versus chaos battle all over again, but in code.
It really is, and the way they approach it technologically is quite clever.
This is where it gets really interesting for me. How does the tech actually work to impose that order?
Well, the Cosmos network itself uses a proof-of-stake system for its own security, but the key innovation for connecting other blockchains is their hub-and-spoke architecture.
Hub and spoke, like an airport.
Exactly like that. You have a central chain called the Cosmos Hub, which acts as the main hub. Then, independent blockchains called zones connect to this hub.
So the zones don't talk directly to each other. They go through the hub.
Primarily, yes. The hub acts as a router and a central ledger that keeps track of the state of the connected zones. This allows zones to securely transfer tokens and data between each other, with the hub facilitating the process. The magic that makes this possible is a protocol called IBC.
IBC.
Inter-blockchain communication protocol. It's the standard they develop for how these different chains can securely send messages and tokens back and forth via the hub.
So instead of isolated digital islands, you get this interconnected network, this digital archipelago connected by the main hub. ordering the blockchain Wild West.
That's the vision. IBC is designed to be trust minimized. A zone sending a message doesn't need to trust the zone receiving it or vice versa. They only need to trust their own connection to the hub and the hub's security. It enables near-instant transfers and communication between vastly different blockchains without relying on potentially risky third-party bridges or exchanges.
That sounds like a major step towards a more unified system.
Yeah.
How is the network itself structured? Is it complex?
It's built with a layered architecture designed for flexibility. There are three main layers. At the top, the application layer. This is where developers build their specific blockchains, their zones. Could be anything, a decentralized finance app, a game, a social network. Each zone has its own rules, its own state.
Okay, the custom chains.
Then there's the networking layer. This is where IBC lives, handling the communication between the hub and the zones, and between zones via the hub.
The connections.
And finally, the consensus layer. This is what ensures all the computers running the software agree on the state of the network, keeping it secure. Cosmos often uses Tendermint Core for this, which is a Byzantine fault-tolerant consensus engine, meaning it can keep running securely even if some validators are faulty or malicious. It provides fast finality for transactions.
And the ATOM token, that's the native token for Cosmos.
Yeah.
How does that fit in? Is it just for paying fees?
It's much more than that. ATOM is crucial for securing the Cosmos hub itself through proof of stake. Token holders can stake their ATOM, essentially locking it up, to help validate transactions and maintain the network.
And they get rewarded for that.
Yes, they earn staking rewards. This aligns the incentives of token holders with the health and security of the network. ATOM is also used for paying transaction fees on the hub, and importantly, it grants holders governance rights. They can vote on proposals about the future development and direction of the Cosmos ecosystem.
So it's the fuel, the security deposit, and the voting ballot, all in one.
A pretty good summary, yeah.
Yeah.
It's the economic backbone of the Cosmos hub.
This whole setup sounds incredibly well thought out for creating digital harmony. But it does bring up an interesting point about decentralization, doesn't it? It relies on this central hub.
It does, and that's a key aspect, a very pragmatic design choice. It offers a nuanced take on decentralization. While the individual zones are sovereign and the goal is a decentralized ecosystem, the hub-and-spoke model does introduce a central coordinating point for security and communication via IBC.
So maybe pure chaotic decentralization isn't always the most practical way to get things working together.
That seems to be the implication here. Cosmos suggests that to achieve a truly harmonious, interconnected system of independent parts, you might need some form of central coordination, some shared infrastructure like the hub, to facilitate secure interaction. It's a balance between autonomy and coordination.
It really does mirror that philosophical tension, doesn't it? How much structure, how much central agreement do you need for a functional, decentralized order?
Precisely. And calling the protocol Cosmos wasn't just clever branding. It was, and is, a declaration of purpose. To forge a unified, orderly, interconnected whole from the often fragmented, sometimes chaotic, pieces of the blockchain world. It's that ancient human drive for Cosmos playing out in code.
And that brings our journey full circle. Wow, we've covered a lot of ground.
We really have.
From Pythagoras drawing that line between order and chaos in ancient Greece, to the mind-boggling scale and mysteries of our physical universe, the Big Bang, inflation, dark matter, dark energy.
And looking at how we try to share that understanding through popular science, like Sagan's and Tyson's work.
We detoured through the surprisingly tangled history of the Cosmopolitan cocktail, finding order imposed in a glass.
Pause to appreciate the simple, natural harmony of the Cosmos flower.
And ended up exploring the complex architecture of the Cosmos blockchain, trying to build digital order.
It's quite a tapestry.
It really is. And the central message, the thread running through it all, seems crystal clear, doesn't it?
That the word cosmos isn't just a label. It's a concept, a driving force.
Exactly.